Alrighty, good morning, lads and ladies. Welcome back to MAC 1140. Let's do the thing. Okay, everything is in this anomalous situation where everything is working as it ought to. Alright, here we go. So today I want to start by talking a little bit about the first test. This is MAC 1140, section 008. Focus. Which is pre-calculus. And today is the 16th of September 2021. So today we're going to talk about the test. And then we're going to cover section 2.7, which is on combining functions. And I don't think we're going to get out of section 2.7 today. We should be able to take care of all of 2.7, but we're definitely not getting into 2.8. So, let's see, I don't have your syllabus out. Let me pop that. Okay. So we are almost ready for exam 1. We mentioned this the other day, right? Exam 1 covers up through section 2.8. Section 2.8 is one section away, which means we are about one class away from finishing all the material that's going to be on the first test. So it's time for us to set the date, the exact date for the first test. Victoria, I'm not sure. We can talk about that after class. Give me just one sec. So, the exam. I think it is most likely that we will finish 2.8 on Tuesday of next week. So the soonest we could have the exam is Thursday of next week. But we could also do it Tuesday the following week. So we're looking at either the 23rd or the 28th for the first test. If we have the test on the 23rd, obviously there's a little bit of less time to prepare between the last day of relevant lecture and the day of the test. There would just be that 2 days. If we have the exam on the 28th, you'll have a little bit more time to prepare, but it means we're going to have to crunch something a little bit later. And the facts of the situation are that the later material is a little tougher. So I think this might be a good place for us to be a little bit conservative with time usage, so you can have that extra study day when it comes to like the second exam, which covers things like rational functions and complex numbers and factoring polynomials. Or the third exam, which covers things like logarithms and exponential functions. But I'm down to let you guys decide. So what I'm going to do here is I'm going to host a poll, and then you guys can vote on the... Oh, what the hell? What the fuck is this? No, get the fuck out of here. Oh my god. Alright, so I'll host a poll, and you guys can decide between the two dates. The two options here are going to be the 23rd, which is Thursday of next week, and the 28th, which is the Tuesday the week after that. Those are the 2 days we can choose from for the test. If we go with the 23rd, it means, we'll finish the material for the test on the 21st, and then you'll have the test on the 23rd. That means the material will be fresh in your mind, but you won't have had like a whole week to practice extra problems if you wanted to. If we do the test on the 28th, that means that I'll have to lecture some fresh material on the 23rd. We can't just have a dead day here, so there would be a lecture involving material that's not going to be on the test on the 23rd, but you would have the weekend to review. And again, my only little note or word of caution to you is if we take that extra time for exam 1, then we won't have that extra time for one of the later tests, and I think it may be worthwhile to kind of hold on to that, so we can use it a little later. But I'm down to let you guys choose, so let me go ahead and launch a poll. What were those dates? 23 and 28. 9/28. 9/23 is next Thursday. 9/28 is the following Tuesday. And you can choose 9/23 and before I launch this poll, let me tell you a little bit about the way proctoring is going to work for the test, because for some of you this may factor in. So there's a question in chat. Let's address that first. Is there any way we could do a review session on the 23rd? This class has so much content that we really can't put a whole day into review. I'm happy to have an office hour that is kind of dedicated to reviewing for the test if you want to set one of those. Then I would be more than happy to do that, but we can't put a whole class day into reviewing for the test. So that's the idea, is that you can review independently, you can review with me in office hours, but cannot put a whole day there. Regarding exam proctoring, here's the way it's going to work. You have two options. The first option is to take the test at the testing center, right? You can go to the campus and take the test in Building N's testing center. If your intent is to do that, you just have to let me know ahead of time. And that means you won't have to deal with HonorLock or any of the other kind of proctoring systems. If you're not going to take the test in the testing center, the other option is this. You'll come to a Zoom meeting just like this one, but you'll do it on your phone. So you'd sign into Zoom on your phone, and then you would set your phone off to the side, somewhere, like way over here, leaned up against a coffee cup on the side of your desk, something like that. If you're going to do that, I have to give you the okay on the Zoom angle before you're able to launch the test, and then you would launch the test using HonorLock. So if you're going to take the test in the testing center, you don't have to do any special proctoring stuff. If you're going to take the test kind of at home or in class proctored by me, you're going to use two systems to proctor. First is going to be Zoom on your phone, and that's going to be set up by you somewhere off to the side where I can see your hands, your desk, your lap, and the paper that you're writing on. And then in addition to that, you'll have to sign into HonorLock, and HonorLock will record your screen, your webcam. And so those are the two systems. So if you were thinking that you might want to take the test in the testing center instead of dealing with all of that proctoring stuff, that may influence which day you want to take the test, depending on whether you have to drive to the college from far away or something like that. A few questions in the chat that I'd like to address. If you take the test on the 23rd, we'll be able to put up a set of practice questions or a practice test or some sort of review. So there will be another quiz. And I can try to get you some extra review problems, but there isn't like a practice test, right? That's not something that I do. Tests done through WebAssign? No, the tests are done in Canvas. They're structured as Canvas quizzes. I don't mind showing you an old test from a different section, like a different class, something like that. I can show you probably shouldn't show you the MAC1140 tests. Let's show you the differential equations test, just so you can see the structure. Okay. So the tests are set up in Canvas as quizzes. And this is what they look like. So there are a handful of true-false questions. Obviously, these are not the sort of questions you would be answering. This is differential equations. There's a handful of true-false questions, each worth 4 points. There's a handful of 4-choice multiple-choice questions, each worth 6 points. And then the majority of the test are free response questions worth 10 points each. The true, false, and multiple choice, you just click the right answer, you get it right, click a wrong answer, you get it wrong. The free response questions, you have to type your final answer in the box, and you have to show your work on paper. And then after you finish the test, but before you leave the Zoom meeting or before you leave the testing center, you have to scan that written work for your free response problems and submit that to a separate assignment in Canvas. All right. So are we all clear on how the tests are going to work and what your options are?
I have a question.
Yeah.
For the ones that we show our work, if say we get that answer wrong, but it's like a sign that we messed up or something, do we get partial credit for it or no?
Absolutely, yeah. That's why I have you show your work. So the correct answer on those free response questions, correct answer is 2 out of 10 points. The bulk of the credit for the problem comes from the written work. So
Okay.
if you solve the problem 90% correct, but then you drop a minus sign at the end or something like that, or change a 3 to a 7, then you're going to lose a half point or a point, something like that.
Okay, and it's hard, like maybe not like a practice test, but like you said, maybe like a set of problems just as like kind of like a review is kind of what I was saying, not like necessarily a practice test, but just like answers or questions maybe from each section that we could go over. I think the homework does that, but
Yeah, I'm not opposed to doing that. WebAssign does have a mechanism in there to help you review specifically the material that you had a hard time with in the homework. Like if you answered a question wrong 2 or 3 times before getting it right, WebAssign does have a mechanism to go back and review those. I could publish an additional thing in WebAssign, like an extra assignment that is optional if you wanted, to kind of serve
yeah,
as a
because
review.
some of the things in the practice or in the web assign, like if it was a question that you had specifically put up or designed, if you had more than 1 or 2 attempts on it and you try and practice another, it'll say that it's not available,
Oh.
that another one isn't available for that. That's why I was asking.
I see. Yeah, that may mean we've like exhausted all the random numbers that they can throw in there without like breaking the question. I'm not sure why that would be the case, but I wouldn't be against putting together an extra assignment in WebAssign. But that would mean more work for you. So it's up to you guys. If that's something that you want, I can do that. Maybe we could make it a low stakes assignment or something.
Okay, thank
So
you.
let's go ahead and knock this out. All right. So we're all clear on what the questions are and what the stakes are, the things you want to think about when you make the decision. I'm going to save the question, launch the poll. There we go. All right, so please go ahead and answer whether you want to take the test Thursday or the following Tuesday. While you do that, I will refresh my coffee. Okay, it looks like the test is going to be on the 23rd. Here are the results.
Also, I have a question, Professor.
Sure.
I was wondering, I know we have an assignment due this upcoming Tuesday. Since the test is going to be on Thursday, are we going to have another assignment or only those practice questions that we just discussed about?
Let me see where we're at. And then there's another question that came in the chat that I'd like to address too. Yes, Chris, the test is during class time. So that's the thing with a hybrid class rather than a fully online class is what's called a synchronous class rather than an asynchronous class. That means that the tests do take place during class time. That's so I can proctor live rather than having kind of a free for all. Regarding the assignments that will be due before the exam, so there will be, let's see, this one, I think I gave you guys a little bit of extra time on this one, right? Rather than having this be due on Thursday, it's due the following Monday because it was kind of a long one. I didn't want to pinch you there. So after today, I will be releasing another 2.7 homework, and then there would be a 2.8 homework either attached to that or separate before the day of the test. So today we are going to knock out 2.7, and then on Tuesday we would knock out 2.8, and on that Tuesday I would be releasing another homework. That would be a homework just focused on 2.8, which would be due Thursday, the day of the test. All right, and then I can create a separate assignment to kind of serve as a review, although I caution against that way of handling things. My advice would definitely be to go back over the homework problems and make sure you're comfy with those rather than trying to pile extra stuff on. So maybe rather than doing that in WebAssign, I'll try to post something to Canvas, something that's not going to affect your homework grades. I'll have to think about how to do that. But yeah, one more homework between now and the test. There will be sorry, 2 more homeworks between now and the test, right? There's the one I'm going to release today, the rest of 2.7, and then there's the one I'll release next Tuesday, which will be 2.8.
If we take it at the testing center, do we have to do it during class time as well, or is it from,
I would give a slightly larger window centered around class time, so like class time plus or minus 2 hours, something like that.
okay.
All right. Any other questions about the test?
I have a question, Professor.
Mm-hmm.
So you said that we would have to set up the Zoom off to the side, no problem. But you said that before we exit Honor Lock, we need to scan our scratch sheet. How would we do that if our phone is on Zoom?
So you don't need to do it before you exit Honor Lock, you got to do it before you leave Zoom. So you can, with Zoom open on your phone, you can open up a Notes app or the scanning app if you're on Android, some other scanning app, and you can run those concurrently while you're there in Zoom with me.
Gotcha. Okay, thank you.
Yeah, no problem.
I don't know if you guys know this, but Adobe Acrobat, or you can download Adobe Scan on your phone, and it's like a free scanner that you can,
Ooh, nice.
it puts it in PDF and everything, and it's for Apple or Android.
That sounds lovely. I really appreciate that, Megan. Up until now, I've been suggesting people use the app Cam Scanner. That's the one I have on my phone, and it does a good job of like enhancing contrast and giving you a PDF. But I do think that there is a free version of Cam Scan, but I think it's got like a limited number of scans or something like that. So um, I appreciate that, Megan. That was just Adobe Reader or
It's no, you don't even need Adobe Reader on your phone. It's just, if you go in your app store, it's called Adobe Scan. It's free and you don't need an account or anything. It just does it.
very nice. All right, yeah.
And Genius Scan is really good.
Okay, Genius Scan, Adobe Scan. So whatever you like, you will need a scanner app on your phone. That's going to be necessary, and you'll need Zoom on your phone if you're going to take the test here, kind of thing, online rather than at the testing center. But it's up to you. You can do this at the testing center. You need to contact me about this. Candace message me. To arrange this. Because I have to schedule for you in advance. The testing center is very busy right now because there's still a lot of classes working online or in the hybrid setting like this. So if you think you're going to want to take the test at the testing center on campus, please let me know as soon as you can so I can reserve a spot for you. They fill up. Or online using Zoom and Honor Lock. And Zoom is going to be on your phone. Okay, so those are our options, and just let me know what you want to do. If you're going to take it at the testing center, you got to let me know. If you're going to take it online outside of the testing center, you don't have to let me know that. But please, if you want to do it at the testing center, send me a message so I can get you a spot reserved there. Okay, I think that's everything we need to talk about for the test, so let's get into section 2.7. So I think I mentioned with you guys last time, I forget, I'm doing too many pre-calculus sections right now. Mathematicians and specifically algebraists are really into studying spaces of functions. And within those spaces of functions, we like to see how the regular algebra operations interact with the sort of things that we're interested in, like domains and increasing and decreasing intervals, stuff like that. So that's what we're going to start playing with. We're going to take just pairs of functions and see how we can mash them up and see what that does to the domain, see what that does to the graph, all of these other good things. One more question in chat there. I do prefer Canvas message over emails. Either one is okay. If you're going to email me, please put the course and the subject in the course and the section number in the subject line. But Canvas message does that automatically, which is great. All right. So the basics. Given two functions, f and g, we can form new functions. And we call these new functions f plus g, f minus g, f times g, f over g, and the big one is f circ g. The little circle here is a composite operator. This is not multiplication, so this is like a little open circle, and we'll explain what these are. But each of these things is a new function, and they're named this. We name this one f plus g because of what it is. It's the function that you define by saying f plus g of x is f of x plus g of x. This is called pointwise addition. So this new function is defined one point at a time to be the sum of f and g. That's why we call it f plus g. And the other ones here are all defined in the obvious similar way. F minus g of x is f of x minus g of x. F times g is defined by the rule f times g of x is f of x times g of x. F over g is what it sounds like. You take f of x and point for point divide it by g of x. And then this last one, f circ g of x. Sorry about that, this is an x. This is defined as f of g of x. And it's that last guy that we're going to be maximally interested in. The others are all kind of just to prepare us for them. One of the fun things to talk about with these guys I mentioned is the domain, right? And I think it's a good exercise to ask yourself what the domain of these functions might be. And I'm going to look first at just these guys, because they don't introduce anything especially weird. So imagine I've got two functions, f and g. I know both of their domains, right? Say the domain of f is there's a notation for this dom f, and the domain of g is dom g. So I'll just name those sets, dom f and dom g, whatever they are. What do you think would be necessary for a number to be in the domain of this new function, f plus g? Imagine you want to plug a number in here. What needs to be true about that number? I realize it's a very open-ended question.
Does it have to be a real number?
Yeah, let's restrict our attention to real numbers. Let's assume that the domains of f and g are both subsets of the real line. How would those two domains, the domain of f and the domain of g, be related to one of these new functions, like f plus g? Well, let me say it another way. Suppose 1, the number 1, is not in the domain of g, but it is in the domain of f. Can I plug 1 into this function?
No.
No, right? Because to plug 1 into this function, I would have to plug 1 into f and plug 1 into g. But if 1's not in the domain of g, I can't do that. So in order for a number to be in the domain of any of these guys, but thinking specifically about this one, it has to be in the domain of f, and it has to be in the domain of g, right? If I'm going to plug x equals 5 in here, then I have to be able to plug it in here, and I have to be able to plug it in here, which means it needs to be in both of these sets. Now, what's the set operation that says I'm going to take just the stuff that's in both of these? Does anybody remember that? So this is kind of off to the side, just saying what the domains of f and g are. How do I say I'm going to take these two sets and just hold on to their overlap? If I put a union symbol in here, would that be describing what I'm asking for? Would that just give me the stuff that's common to both? No, right? There could be like maybe 1 is in here, but it's not in here, and then 1 would be in the union. That's not what I want. The operation, the set operation, is an intersection. So the upside down union symbol means I'm going to take just the overlap, right? In the Venn diagram, the union is the thing in the very middle. It's the stuff that's common to both. The domain here is a little different. Certainly, the same rule is true. Like, if 1 is not in the domain of f, then I cannot plug 1 into this. So it has to be some subset of this. But then we have to throw away any x's such that the denominator is 0. And this symbol, backslash, is sometimes called set minus. It's like, you know, take this set and throw away this shit. The domain of the composite is more complicated. This is harder. So in order to plug a number in here, what does that even mean? Well, that means I'm going to plug that number into G, take the output from G, and then plug that into F. So here, the domain is harder to discuss. But it has to be a subset of the domain of G, the inner function. Right? In order to plug a number into that last guy, I have to begin by plugging it into the inner function. And if I can't do that, I'm dead in the water. But the outer function may also have an impact on the domain. So I think the right place to start here is just with a few simple examples to make sure you guys are comfy with the definitions. And then we'll do some slightly more complicated algebra stuff. Oy vey. So let's do it like this. Draw some graphs. One will be the graph of f of x. Okay, and then a graph of G. How about let's do something like this. We can do something over here. Yeah. Actually, let me change this to a -2 down here. That looks like it's a little further away, doesn't it? Alright. Is that everything I could want? I think it is. Okay. So let's find f plus g of 0, f minus g of 1. Make sure this is clear. That's 1. This is 2. This is 3. What else? We could do g of -1. And about f circ g of 3. And maybe we'll do one more. G circ f of 3? Sure. Alright, so I'll keep the graph up here as we walk through these. Any idea how we could compute f plus g of 0? How do I get started with this very first piece?
Do we plug in 0 to both functions?
Yeah, that is going to be the case. And the way I would recommend writing this is first just use the definition. Right? This is a great first step, just writing f plus g of 0 is f of 0 plus g of 0, because that tells you what to do. And what Ashley said is exactly correct. We're going to plug 0 into both functions and then add them up. Okay, what is f of 0?
-1.
Yeah, very good. F of 0 is -1, right? Here's the graph of f of x. F of 0 is the y value when x is equal to 0. So x equals 0 is here on the x-axis. The y value on the graph there is -1. Okay, what is g of 0?
0.
0.
Yeah, right? G of 0 goes right to g goes right to the origin. So that's -1 plus 0, which is -1. Alrighty. What about f minus g of +1?
You would plug in the 1 again.
Yeah, here I'm looking at f of 1 minus g of 1. Alright, so we're going to begin with the definition always. And then I know what I'm looking for. Okay, I'm looking for f of 1, and I'm looking for g of 1. Well, f of 1, that's 0. This minus is this minus. And then g of 1, that's 1. So this would be 0 minus 1. Ah, it's -1 again. That wasn't on purpose. We comfy with these first two bits? Are there any questions about these, or how we knew what to do? Okay. F times g of -1, by definition, is f of -1 times g of -1. F of -1, from the graph of f, we see over here, when x is -1, the y value on that graph is 0, right? So f of -1 is 0. And that means it doesn't really matter what g of -1 is, right? No matter what g of -1 is, this is going to come out to 0, but we can take a look on the graph of g. G of -1 is -2. So this would be 0 times -2, which is 0. Well, good so far? Now, these last two take a little bit more love, so let's think carefully about this. Even if we had no idea what to do with these first three, we can write down the definition, and that's a good way to get started. Here, let's do the same thing. So f circ g of 3 is f of g of 3. Alright, how could I possibly compute this? What information do I need in order to get this done? I see there's something in chat there.
The value of g of 3.
Yeah, very good. Very good. Dylan's exactly correct there. What I need to get started here is this inside thing, g of 3. And then I can try to find f of that. There's a question in the chat for the first one. How do you know the x value in g of x if there are more points? So on this first guy, remember I'm looking for there is an x value already plugged in the question. They're saying find f plus g of 0. So if they didn't tell me they want this thing evaluated at 0, then I couldn't do it. But I can tell what g of 0 is, and I can tell what f of 0 is, so we can compute this just fine. Is that maybe what the question was getting at? The question in chat? Okay, cool. Yeah, if you don't know what the points on the graph here are that correspond to the values they ask you to plug in, then you really are dead in the water. There's nothing you can do. All right, so down here we said, in order to get started, we need g of 3. In other words, this sort of thing is always computed from the inside out. And that can be a little bit complicated because we read in English from left to right. But here it's really g of 3 that happens first, and then we're going to do f to that, right? Because this is f of g of 3. So what is g of 3?
-2.
Very good. G of 3 is -2, which means this thing is f of -2. And then f of -2, can look on the graph for f.
3.
Yeah, that's 3. Neat, right? All right, let's do the last one. How about g circ f of 3? Well, that would be g of f of 3. Oh, did I not? So this is my poor construction. And it's maybe a good example of what Chris was asking about in chat. F of 3 is what we would need to get started here. But I haven't actually specified f of 3, have I? So this isn't one we can do. We look here on the x-axis where x is equal to 3, and I don't have a clue what that is. Let me modify this then a little bit. My apologies. Yeah, I wrote this down without thinking too carefully. Let's compute g of 3 instead. Oh, and I'm going to have to modify something for that, but oh no, I don't. No, I just have to label this. Okay. Alright, so let's find g of 3. From the graphs I've given you, we can actually do that. We have to get started by saying, okay, this is g of 3, working from the inside. And then I look on the graph of g. When x is equal to 3, g of 3 is the y value here, which is -2. So whatever this is, it is g of -2. And then I look back on the graph of g. When x is equal to -2 over here, the function g is going through the x-axis. That means y is equal to 0 there. So g of -2, that's 0. Alright, any questions on these first few examples? How we're using the graphs to do this? Okay. Other variations on this sort of thing that we can do, working just algebraically, I could ask you to compute f plus g of x, f times g of x, f over g of x, and f circ g of x, and their domains. Where f of x is, let's do something fun. How about x over x plus 1, and g of x is about 1 minus x squared. So just grabbing a few of the combined functions, and we'll be able to see the relationship between the domains. I think it's worth noting the domain of each on their own at the start, so we can compare to the claims I made at the start of class. The domain of f here, this guy, would be everything except what makes the bottom 0, which is -1. So this is negative infinity to -1, union with -1 to infinity. And the domain of g is all real numbers, negative infinity to infinity. So just to start, since we're being asked for domains of these combined functions, it's good to have the domains of the original in hand. F plus g of x. Again, you just start with the definition. F of x plus g of x. What is f of x? That's x over x plus 1. What is g of x? It's 1 minus x squared. And you could have a common denominator here, but it's not necessary, right? If you're just asked for this thing and its domain, you can read off the domain from this, right? You just, all the same rules that we've been using throughout the rest of the semester. You look for red flags. The only red flag present here is the same red flag that we saw in f. Right, the only restriction in this function is coming from the denominator of the first piece. So the domain here is the same as the domain of f. And you'll notice that is the intersection of these two sets. If you ask what's common to these two sets, what is the overlap, the domain of g is all real numbers. The domain of f is all real numbers except -1. So if I ask what's common to those, it's everything except -1. What's the overlap between those sets? It's precisely the domain of f. F times
Would that be only true in equations like this where there's a fraction or a denominator?
Yeah, so the idea that the domain of the combined function is the intersection of the domains of the original functions, that's true for the sum, the product, and the difference. And then the quotient, this guy, and the composite, this guy, both have slightly more complicated rules. So the first guy, f plus g, if we trust the rules I gave you at the beginning of class, right, we said f plus g, f minus g, and f times g should all have the same domain, just the overlap of the domains of the original two functions. So we should find that when we compute this guy, his domain is the same. And if we're not doing the difference here, but if we did him, the domain should be the same there as well. But the domains for the quotient and the composite we expect to be a little more complicated. So f times g, that's just f of x times g of x. F of x is still x over x plus 1, and g of x is 1 minus x squared. Now here's an important thing. This expression should be in parentheses, because we're multiplying the whole of that expression by the whole of this expression. The only reason I'm not putting parentheses around this fraction is because, remember, fraction bars always imply parentheses top and bottom. So if this was an expression with multiple terms, like, you know, x plus 7 or whatever, I would put that whole thing in parentheses also, because I want to multiply all of the function f by all of the function g. So when you're doing these, even if you're not sure if you need them, probably good to start by writing them like this. Right, that'll make sure that you don't make any little missteps with distribution. Again, like in the previous one, it's possible for us to combine these into a single expression. It's not necessary for finding the domain, but I don't think it's a bad thing. So let's go ahead and take a look. Remember, 1 minus x squared is the same as 1 minus x squared over 1. And when you multiply fractions, you multiply them straight across. So if I wanted to write this as a single expression, it would be x times 1 minus x squared all over x plus 1. And we can stop here and find the domain. the point I want to make is that, well, actually, let me go a little bit further here so I can drive it home. 1 minus x squared factors. This is something that for sure you've seen in a previous algebra class. It's 1 minus x times 1 plus x. So I could write this expression like this. Alright, factors as a difference of squares. If you haven't seen that factoring trick before, don't panic. I will be showing it to you when we get to the section on polynomials. And then x plus 1 downstairs is the same as the 1 plus x upstairs. We can cancel these. This is valid. But I can only cancel those if that factor is non-zero. Right? 0 over 0, you cannot cancel those because the 0 downstairs makes things undefined. So when we do this step right here, we always make a note. This is for x's besides negative 1. Because if x is equal to negative 1, then the factor downstairs is 0 and the whole expression is undefined. So the basic idea that I'm trying to drive home here is that you cannot cancel 0 over 0, right? And this expression, it's possible to end up in the form 0 over 0 if you plug the wrong x values in. If you were to plug negative 1 in for x here, the top would be negative 1 times 2 times 0, which is 0, and the bottom would be negative 1 plus 1, which is 0. And then you'd have 0 over 0, and that's a fucking problem, right? Like, we cannot divide by 0. So this cancellation is valid only as long as the factor you're canceling from the bottom is non-zero, only as long as x is not equal to negative 1. The reason I say that is because if you look for domain red flags here, in the fully simplified version, there are none, right? No variables in the denominator, no variables under roots. But if you look for domain red flags here, or here, before we did any cancellation, there is one, right? This x plus 1 downstairs. So you should stop at a step like this. To find the domain. And I know I'm still going to get lots of questions about this, but I want to try and head those questions off as best I can. This is the one thing that gets people in trouble in section 2.7. Finding domains of combined functions. You gotta stop before you cancel anything to find your domain. That's the safest way to do it. If you are careful as you go through this procedure and every time you cancel a factor you say, oh yeah, that factor can't be 0, then you could do that too. I could say the domain of this is all real numbers, but I'm only allowed to call that function x times 1 minus x for x's which are not equal to negative 1. So as long as you make this note, you could still get the domain from here. You could say, okay, this guy has no domain restrictions, so his domain would be all real numbers, but the function is only equal to that if x is not equal to negative 1. So as long as you have all of that content, then you could state the correct domain. But most often people do something like this, they cancel, they get here, they say, oh, the domain of this should be all real numbers, and then WebAssign goes, eh. And you go, why? I know the domain of this is all real numbers. Oh, well, because you canceled a factor. You canceled a factor that would have made the original expression undefined. So it's best to stop before you factor or cancel anything to find your domain. Stop no later than here to find your domain. And at this step, I can see there is a red flag. I know again that x plus 1 can't be 0, so x can't be negative 1. And we see that the domain here is negative infinity to negative 1, unioned with negative 1 to infinity. And that's what it's supposed to be. Remember? We said the domain of f times g should be the intersection of the domains of f and g. And that's what it is. That's what this is. But you can get yourself into trouble by canceling factors before you find your domain. So find your domain before you cancel anything. That's the rule. I'm going to say it one more time.
Professor?
I always get so many emails about this. So just one more time. Before you find your domain on any of these problems, check and see what step you're at in the simplification. Find your domain before you cancel anything. All right, yeah, Zane?
Yeah, sorry about that.
No, what's up?
I have a doctor's appointment in like 13 minutes. Could I leave
Oh,
early?
please, yes, go
Yeah.
to the doctor. Just watch
Okay.
the video later, okay?
Yes, thank you so much. I appreciate you.
Of course, of course. All right, moving on. F over G. This is the first one whose domain rules are more complicated. The good news is you don't have to memorize that weird set minus domain rule. You can just write the thing down, don't cancel anything, and then apply the usual domain rules, right? Looking for red flags. So f over g of x is f of x over g of x. That's definitely always true. And I'm gonna come out here to the side a little bit. F of x is x over x plus 1. G of x is 1 minus x squared. And here there's lots of things that can go wrong. Again, using parentheses like this is important when you have a sort of compound fraction, a fraction within a fraction. Make sure it's clear sort of which one's the big fraction and where's the top, where's the bottom. And again, before you try to simplify anything here, this is the step where I would recommend stopping and finding the domain. So what sort of domain red flags do I have here? Well, I've got this x plus 1 in the denominator of the little fraction. So I know that's not allowed to be 0. And I've also got this 1 minus x squared in the denominator of the big fraction. So I know that's not allowed to be 0. And each of these we have to solve. So x plus 1 equals 0 if and only if x is negative 1. Alright, so I got to kick negative 1 out. And then 1 minus x squared is equal to 0 if and only if I can just add x squared to both sides, right? 1 is equal to x squared. And then I can take square roots on both sides. Remember, when you do that, you get a plus and a minus. And the square root of 1 is 1. So that's plus and minus 1. So, from this guy, x is not allowed to be negative 1. And from this guy, x is not allowed to be either positive or negative 1. So our domain is all real numbers except x equals plus or minus 1, which in interval notation is negative infinity to negative 1, unioned with negative 1 to positive 1, unioned with positive 1 to infinity. Remember, the number of union symbols is equal to the number of points removed from the line. So if I'm plucking out the two numbers, plus and minus 1, I should have two union symbols. Isabel asked a good question. When do we use the inverse U, the upside down U, the intersection? That's to describe the commonalities between any two sets. So maybe just off to the side somewhere here, I'll describe the intersection operator. First, let's finish this, right? I'll go into a little more detail about what intersection is later. It's pretty rare. It's pretty rare that the nicest way to describe a set is as an intersection of other sets in this class. But it is good for you to know, so we'll talk about it. But first, let's finish up the last one, right? So are there any questions about how we found any of these three functions or their domains? Victoria, the domains for addition, subtraction, and multiplication are all the same. The domain for division, tiny bit more complicated, because you got to make sure the function on the bottom is not 0. And then the domain for the composite is totally different. But addition, subtraction, multiplication will all have the same domain. All right, we can simplify this a little further. That's x over x plus 1 times the reciprocal of 1 minus x squared. Zoom back and down here. So continuing this expression here, I could rewrite this as x over x plus 1 times 1 minus minus x squared like this. And there is actually a little more that we could do with this if we wanted to. If we wanted to factor this as 1 minus x times 1 plus x, we could. But there's no need to. You know, this is quite fine. All right, last call for questions on these three. All right, let's do the intersection then. So we wanted f circ g. Let me do this. So the composite function f circ g is defined to be f of g of x. And there's kind of two ways you can go about writing such a thing down. I recommend plugging in the inside. So what's the inside here? It's 1 minus x squared. So what is this thing? It's f of 1 minus x squared. And think back to that first homework where I had you guys computing f of 1 minus a, or f of a plus h, or f of x squared. That function notation is, again, really critical here, right? This looks like, after you go through this kind of obvious definition step, this looks like a problem from your very first homework set, right? You guys recognize this sort of thing? So how do we find f of 1 minus x squared? I've got the definition of f. How do I find this?
Converting 1 minus x squared to f of x.
I could only hear the very end of that. Can I ask you to repeat that, Genesis? I'm sorry.
Again, 1 minus x squared to the x values of f of x.
Yeah, we look at this thing, and everywhere there's an x, here and here, we'll write parentheses 1 minus x squared. The kind of crude way I've told people to remember this is that, remember, f of, you know, a would be a over a plus 1. F of some shit is that shit over that shit plus 1. F of your mom would be your mom divided by your mom plus 1. F of anything is what you get by plugging in for x that thing. And if we're being careful, we should do it in parentheses. So I know the humor is crude, but it works. So here, f of 1 minus x squared would be 1 minus x squared divided by 1 minus x squared plus 1.
Would you be able to cancel the 1 minus x squared out just to get the 1?
Good question. So is there a factor of 1 minus x squared in the bottom? It's a valid question.
Yes.
There's definitely a factor of 1 minus x squared upstairs, right? This whole numerator is 1 minus x squared times 1. But downstairs, I've got 1 minus x squared plus 1. And remember, addition and subtraction, they kind of mess with cancellation, right? So I would need to extract a factor of 1 minus x squared from the bottom. I would need to be able to factor this expression out from the bottom in order to cancel it. So at least in the state it's in right now, I cannot cancel these. But if, after combining like terms down here, you're able to factor 1 minus x squared out, then you could cancel. So in the state it's in right now, the answer is no. But we can check. So kind of really just following order of operations here, right? Remember, the top and bottom of fractions always have big parentheses around them, so I should try to simplify the top and bottom, then try to factor, then cancel. So unless your immediate previous step was factoring, don't cancel. The top is 1 minus x squared. The bottom is 1 minus x squared plus 1. And downstairs, 1 minus x squared plus 1 is 2 minus x squared. So what we see is that the factors at the top and the factors at the bottom are actually completely different. We can factor the top and we can factor the bottom. I'll go ahead and share with you the factoring trick. I used it once earlier, we're using it again. This is called the difference of squares. This says an expression of the form a squared minus b squared can always be written as a minus b times a plus b. This is what I use to write 1 minus x squared as 1 minus x times 1 plus x. If we apply that to this expression, factoring the top, I get 1 minus x times 1 plus x, as we did before. Factoring the bottom, 2 is not a perfect square, right? This 1 is 1 squared, is a perfect square. But 2 is not a perfect square. It is, however, the square of the square root of 2. I can factor the bottom as root 2 minus x times root 2 plus x. And now with everything factored, top and bottom, we see that there really aren't any common factors. So remember, before you try to cancel, you gotta factor everything. And if you're gonna factor stuff, you gotta first follow your order of operations and combine like terms. So there's sort of an order to these operations, right? The order of operations. And as long as we follow that, we'll be safe. So if you're tempted to cancel, factor first. If you've got a common factor, then you can cancel.
Where did you say that the root of 2 came from?
It's coming from this difference of squares rule. So 2 minus x squared doesn't look like a difference of squares, does it? But everything is the square of its square root. Right? So now, following this formula, a squared minus b squared equals a minus b, I get the root 2 minus x times root 2 plus x.
Oh, okay, I see.
It's a silly trick, but it's surprisingly useful, and I'm happy that we're looking at this now, because we'll be using it a lot when we talk about polynomials, and I think it'll save you some time if you're comfortable with it. Does everybody see where these two factors downstairs come from? I know it's a little weird. Okay. We haven't found the domain yet, right? So the answer is no, there isn't really anything we can cancel here. But that's not a problem. That's actually good news for us because we know canceling can mess up our domain finding procedure anyway. But how do we find the domain? Let's do it over here. Well, I know the bottom's not allowed to be 0, right? You can think of it as coming from this line if you like. So the red flag is the 2 minus x squared. I know that's not allowed to be 0 because that's what's downstairs. And 2 minus x squared is equal to 0 if and only if. You can add the x squared to both sides. 2 equals x squared. And then take square roots. And you get plus and minus the square root of 2 is equal to x. And that's actually, one of those is coming from this factor, and one of those is coming from this factor. You can think of it either way. So our domain is all real numbers except x is equal to plus or minus the square root of 2, which in interval notation is negative infinity to the negative square root of 2, unioned with negative square root of 2 negative square root of 2 unioned with positive square root of 2 to infinity. I like the question so much I want to come back to it again. Another way to think about whether you can cancel these or not is to imagine just having some number here and having some number here, that same number here. So if this is like 5, then this would be 5 over 5 plus 1, which is 5 over 6. And I can't cancel a 5 from that, right? 5 over 6 doesn't simplify. Precisely the same reason why this can't be canceled. There's a question in the chat, when we have a fraction, do we only look at what's in the denominator? When you're trying to find the domain, yeah. Remember, we've got kind of 2 domain red flags that show up when we're looking at expressions of the type we've seen so far. The first is variable stuff under a square root or any other even root, and then we need to make sure that the inside of that even root is non-negative. And the other is having any variable stuff in the bottom of a fraction, and in that case we need to make sure those things are non-zero. If there's a square root in the denominator, you need to think of those as 2 separate red flags. So if you've got a square root with some variables and all of that is downstairs, first you need to make sure that the thing inside the square root is non-negative, and then second you need to make sure that it's non-zero. Square root in the numerator, same sort of thing. Again, treat them separately. So if you've got the square root of some variables upstairs, find the restriction that comes with that. And if you've got some variables in the bottom of a fraction, find the restriction that comes with that. And then the intersection, the overlap of those 2 sets, will be your domain. So this brings us back to the question about intersections and unions. And I realize it's possible that not everybody has seen the Venn diagram thing, so let's do that. Okay, if I have 2 sets here, the first set is A and the second circle is B, then the intersection of those 2 sets is this. And the union of those 2 sets is everything. So I think this is the cleanest way to describe what an intersection is. It's just the overlap between those 2 sets. And this connects with Victoria's question in the chat. So if you've got a square root in the numerator of some expression, and that tells you, okay, from the square root, you're only allowed to plug in stuff from the set A, and then you've got some other domain red flag, like variables downstairs, and that tells you you're only allowed to plug in stuff from the set B, then the domain of that whole expression would just be the stuff that satisfies both. Has to make the square root happy, has to come from the set A, and it also has to make the denominator happy, has to come from the set B. So you would take the intersection or the common elements of those 2 sets to find your domain. If you look back at the second homework, I think it was, we had lots of questions like that, and we could work some stuff like that in order to prepare, but that would be a better thing to do in office hours. Okay. So these are the algebra rules, right? These are how we work with these symbols. But what do they mean? Is there a nice way to understand these things? And you know the way mathematics tends to build. The answer to that is definitely yes, and we will do shit with that understanding. So what I'd like to look at now is the machine diagram interpretation of the composite function. So how do I say this? Let's say recall. We can conceptualize a function f with a machine diagram. Remember we had like mapping diagrams, machine diagrams, verbal descriptions, graphical descriptions, a bunch of different ways to think about functions. The machine diagram is really useful here. So the machine is f, it's the function we call f. And you can think of f as being like a machine in a factory on an assembly line. Shit comes in over here, shit goes out over here. So shit comes in, f does something to it, and then sends it out. The things that come in are the inputs, the x's. And the things that come out are the outputs, or the f of x's. So f might be the machine that adds 3 to x, right? So, 5 comes in, 8 comes out. 10 comes in, 13 comes out. The machine f just takes whatever you feed it and it adds 3. Or it might be the machine that takes the square root, right? 4 comes in, 2 goes out. 9 comes in, 3 comes out. But this function takes an input, rearranges it somehow, and then sends out a specific output associated with that input. The composite function, f circ g, can be understood in terms of machine diagrams. So I found that the nastier metaphors tend to stick well in the brain. So again, I apologize for being crude here, but the composite f circ g is the, and I don't know how long I'm going to keep being able to use this, is the human centipede of machine diagrams. I think that movie is still present in the consciousness of most humans, right? If you're not aware of this, Google it somewhere private. Not here. What I mean by that is that we're chaining two machines together, and the output from one will be the input for the other, just like the human centipede. So this particular composite, f circ g, f first, then g in this notation, remember, you have to figure out the inside first, so g is really coming first in that. And then the g machine takes in the x and spits out the g of x. And what I'm going to do is I'm going to sew this to the mouth of the f machine. And then what's going to come out? Well, if the f machine takes in x's, it spits out f of x's. If it takes in g of x's, it's going to spit out f of that, which is f of g of x. Alright, so yeah, this whole thing, if you kind of think of all this as being in one box, so I stitch these two machines together, and then I put the whole thing inside one box. That whole thing is the f circ g machine. So you see x's come in, f of g of x's come out. That's precisely what that thing does. If you have a complicated procedure that can be broken down into simpler procedures, this is a really good metaphor for that, right? Like if you're going to square the number and then add 5, you can think of g as being the squaring function and f as being the add 5 function, then this whole thing would be the square then add 5 function. Or if you want to think of g as the put on your socks function and f as the put on your shoes function, then f circ g is the put on your socks and shoes function, right? A barefoot comes in and a socked and shoed foot comes out. You can be very abstract with this, and mathematicians often are. But in our cases, we're focusing on functions of real numbers. Yeah, I enjoy this. It's just gross enough to get people to remember. So there's a kind of interesting question that's related to this way of thinking. Given a function f, like the f machine up there, is it possible find another function which exactly undoes whatever f does.
That just be like an inverse kind of thing where it takes the same machine and does it backwards.
That's precisely it. Yeah. So the question that Megan nailed it. The answer to this question is yes, in some cases, and the name of that thing is the inverse of the function f. And one great way to visualize the inverse of the function f is to just imagine this machine running backwards. So the answer is yes, under some restrictions. On the type of function. We can undo. All right. So in order to kind of think about that answer, I would say this. Like imagine you've got a factory for whatever reason, recycling plant, whatever, and you're recycling aluminum cans, soda cans, beer cans, whatever. You've got a machine, and what it does is you hand it in a can, and it burns all the paint off, and then it outputs the bare can. The machine that would undo that, at least in theory, would take the bare can and then repaint it, right? And send out the original painted version of the can. But if you've burned all the paint off the can, you don't know which can is which. The machine doesn't know whether to paint this as a Coca-Cola can or a, whatever, Pepsi can. In other words, if your function outputs the same thing, regardless of the input, it's going to be hard to find a way to undo that, because you don't know which of those outputs came from which input. If I've got my burn the label off machine, I can look at the input pile and say, oh, Coke, Pepsi, Sprite, whatever. If you look at the output pile, it's all just blank cans. I have no idea which one was a Coke or a Pepsi or whatever. This is getting at the notion of one-to-one-ness, what it means for a function to be one-to-one. So if every input goes to the same output, you're going to have a very hard time undoing that, because you don't know which output to send back to which input. But if every input goes to its own distinct output, then you can for sure say, oh, okay, this one came from over here, this one came from over here, right? If I burn the paint off, but then I stamp Pepsi on the bottom of the can, you know to repaint that as the Pepsi can. All right, I think we are about out of time, and that's okay, because that's exactly where I wanted to end. So this is the end of section 2.7. 2.7 is really just about finding combinations of functions. And then in 2.8, we're going to talk about one-to-one functions and their inverses, and that's this answer to the question. The detailed answer here is yes, but there are some restrictions. That restriction is that the original function has to be what's called a one-to-one function, and I'll define that for you next time. Alrighty, guys? Any burning questions before we go?
I do have a question just related to class. I won't be able to attend office hours tomorrow. Do you happen to have any office hours today by any chance?
Today, no. I don't have any office hours scheduled for today. But if you do, you can send me an email. We can try to set something up outside the normal office hours.
Okay, awesome. Thank you, Professor.
Of course. Okay.
Have a good day.
Yep, of course, you too. Remember, tests next Thursday, right? Week from today, the 23rd. And if you need anything, you can send me a Canvas message, Discord, or email. That is it. Take care, guys.
Thank you.